When I look at a galaxy, even in my mind's eye, I do not see just the bright spiral arms or the glowing central bulge. I also see a massive, invisible structure wrapped around it, extending far beyond the visible stars. That invisible structure is what we call a dark matter halo, and it is not a minor detail. It is the main gravitational scaffold that holds the galaxy together and shapes how it forms, how it moves, and even how it will evolve over cosmic time. In this monologue, I want to walk through how we know dark matter is there, what role it plays in galaxies, how it ties into dark energy and cosmic expansion, and what we still do not understand. Let me start with a simple observational puzzle. If I take a spiral galaxy and measure how fast its stars and gas rotate around the center at different distances, I can build what is called a rotation curve. Newtonian gravity tells me that beyond where most of the mass is concentrated, orbital speed should fall with distance, roughly like the square root of 1 over radius. That is what happens in our solar system. Jupiter orbits slower than Earth, Saturn slower than Jupiter, because most of the mass is in the Sun at the center. If galaxies were just big versions of the solar system, with most of the mass where the light is, the outer stars should orbit more slowly. But when astronomers started measuring galaxy rotation curves in detail, especially in the 1970s and 1980s, they found something else. The rotation speed does not drop off in the outer regions. It often stays roughly flat or even rises slightly, far beyond the visible disk of stars. That means that as you go out, the amount of mass enclosed continues to grow, even where there is very little light. The simplest explanation is that there is a lot of extra mass that does not emit light. That is dark matter. This is not a one-galaxy fluke. We see flat or slightly rising rotation curves in many spiral galaxies. We see similar mass discrepancies in elliptical galaxies, using different methods like the motions of stars and gas, or the temperatures of hot X-ray emitting gas. We see it in dwarf galaxies, which are small and faint, but often dominated by dark matter. So the first way dark matter shapes galaxies is very direct. It provides most of the gravitational pull that sets the orbital speeds of stars and gas. Without that extra mass, the outer parts of galaxies would not be gravitationally bound. They would fly apart over billions of years. We also see the influence of dark matter on larger scales, in galaxy clusters. In the 1930s, Fritz Zwicky studied the Coma cluster and found that galaxies in the cluster were moving so fast that the visible matter could not hold them together. He inferred there must be much more mass, which he called Dunkel Materie, dark matter. Decades later, with better data and new tools, we confirmed that clusters, like galaxies, sit in massive dark matter halos. We map these halos today using gravitational lensing. When light from a distant galaxy passes near a massive cluster, the cluster's gravity bends the light and distorts the image. By measuring those distortions statistically, we can reconstruct how mass is distributed, including the unseen mass. The lensing maps line up with the idea that most of the mass is dark, not luminous. So we have multiple, independent lines of evidence. Galaxy rotation curves, motions of galaxies in clusters, gravitational lensing, the way hot gas sits in cluster potential wells. All of them point to the same conclusion. There is a lot more gravitating matter than we can see directly. When we add up all the evidence, we estimate that about 85% of the matter in the universe is dark matter, and only about 15% is normal baryonic matter. Protons, neutrons, atoms, stars, gas, dust, planets, and you and me. Dark matter dominates the mass budget, and that dominance is crucial for how galaxies form in the first place. To understand that, I need to step back to the early universe. Shortly after the Big Bang, the universe was hot, dense, and very smooth, but not perfectly smooth. There were tiny fluctuations in density, at the level of 1 part in 100,000. We see those fluctuations imprinted in the cosmic microwave background, the afterglow of the Big Bang. Satellites like WMAP and Planck have mapped these temperature variations across the sky with high precision. Those maps are a snapshot of the universe when it was about 380,000 years old. They tell us how much dark matter and normal matter there was and how clumpy it was. In that young universe, normal matter was tightly coupled to radiation. Photons scattered off free electrons, and that pressure of radiation resisted gravitational collapse. Dark matter, on the other hand, did not interact with light. It felt only gravity. So dark matter could start to clump and grow structures earlier and more efficiently than normal matter. Over time, those tiny dark matter overdensities grew into larger and larger halos as gravity pulled more dark matter in. These halos are like gravitational wells. Once they form, they attract normal gas. The gas falls in, heats up, cools, and eventually forms stars and galaxies in the centers of dark matter halos. This picture is not just a story. We test it with large cosmological simulations. In these simulations, we start with an initial distribution of dark matter and normal matter consistent with the cosmic microwave background data. We let gravity act over billions of years, sometimes including hydrodynamics and star formation recipes for the gas. The dark matter forms a cosmic web, filaments, sheets, and nodes where halos grow. Galaxies form inside those halos, at the intersections of filaments. When we compare the large-scale distribution of galaxies in surveys, like the Sloan Digital Sky Survey, to the distribution of matter in these simulations, we see strong agreement. The observed large-scale structure matches what we expect if dark matter is cold, collisionless, and dominant. So dark matter shapes galaxies in a second, deeper way. It sets the initial conditions and the gravitational landscape in which galaxies can even exist. Without dark matter, or with a very different kind of dark matter, the pattern and timing of galaxy formation would change. For example, if dark matter were hot, like very fast-moving neutrinos, it would smooth out small-scale fluctuations. Galaxies would form later and on larger scales. But we see many small galaxies and early forming structures, so that scenario does not match observations. The success of cold dark matter in explaining the cosmic web and galaxy clustering is one of the main reasons most cosmologists accept dark matter as a real physical component of the universe, not just a mathematical trick. Inside individual halos, the detailed shape of the dark matter distribution also matters. Simulations of cold dark matter predict that halos have dense central regions, called cusps, where density rises steeply toward the center, and more diffuse outer regions that fall off roughly as 1 over radius squared or faster. When we model galaxy rotation curves with such halos, plus a disk of stars and gas, we can often match the observed speeds quite well. But not always. In some dwarf galaxies and low-surface brightness galaxies, the inner rotation curves rise more slowly than a cuspy profile would suggest. This has led to the so-called cusp core problem. Some data suggest that the dark matter distribution in the centers of these galaxies is more like a constant density core than a sharp cusp. There are two broad ways to address this. One is to modify the nature of dark matter itself. For example, by considering self-interacting dark matter or warm dark matter, which can redistribute energy and flatten the inner profile. The other is to keep cold dark matter but include more realistic physics of normal matter. Repeated bursts of star formation and supernova explosions can push gas in and out of the central regions, which can, through gravity, heat and rearrange the dark matter. In high-resolution simulations that include strong feedback from stars, cusps can be transformed into cores in some galaxies. Observationally, this situation is still under active study. The inner structure of dark matter halos is one of those places where small-scale galaxy physics and fundamental dark matter properties meet. Another way dark matter shapes galaxies is by controlling how they merge and grow. In the cold dark matter model, structure formation is hierarchical. Small halos form first, then merge to build larger halos. Galaxies inside those halos also merge. The dark matter halos set the merger rate, the typical orbits, and the gravitational potential in which tidal forces act. When two galaxies fall toward each other, their dark matter halos interact gravitationally, creating tidal tails and bridges, and eventually merging into a larger halo. The stars and gas respond to this changing potential. They can be flung out, funneled to the center, or stirred into new orbits. The result can be a transformation from a thin spiral disk into a more spheroidal elliptical galaxy. The dark matter halos act as the massive extended envelopes that absorb orbital energy and angular momentum during these encounters. We see the fingerprints of this process in the stellar halos of galaxies. Around the Milky Way, we see streams of stars, remnants of smaller galaxies that were torn apart as they fell into our halo. The paths of these streams trace the underlying gravitational potential, which is dominated by dark matter. By mapping the positions and velocities of stars in these streams, using surveys like Gaia, we can infer the shape and mass of the Milky Way's dark matter halo. Is it spherical, oblate, prolate, lumpy? The answer affects how satellites orbit, how gas flows, and how the disk might warp. Right now, the evidence suggests the Milky Way's halo is not perfectly spherical. It may be somewhat flattened and may contain substructure, smaller dark matter clumps that never formed many stars. Those subhalos are another prediction of cold dark matter. A big halo like the Milky Way's should contain many smaller dark matter clumps orbiting inside it. Some of those host visible dwarf galaxies. Others may be almost completely dark, with too little gas and star formation to be easily detected. These subhalos can perturb stellar streams and disks, leaving subtle signatures. They are one of the most direct ways to test the granularity of the dark matter distribution. If we found far fewer subhalos than predicted, or a very different mass spectrum, that would challenge the standard model of dark matter. So far, I have focused on dark matter, but the user instructions asked for a strong focus on dark energy and cosmic expansion as well. And those are not separate stories. Dark matter and dark energy both shape galaxies, but on different scales and in different ways. Dark matter pulls things together. Dark energy pushes the universe apart, or more precisely, it drives an accelerated expansion of spacetime. Observationally, we infer dark energy from several sources. The most famous is the study of distant Type 1a supernovae in the late 1990s. These supernovae act as standardizable candles. When we measure their brightness and redshift, we find that the universe's expansion is speeding up, not slowing down under gravity as we once expected. This acceleration is well described by adding a cosmological constant term, or something similar, to Einstein's equations of general relativity. When we combine supernova data with measurements of the cosmic microwave background and the large-scale distribution of galaxies, we get a consistent picture. The universe today is about 5% normal matter, about 27% dark matter, and about 68% dark energy in terms of energy density. Dark energy does not clump on galaxy scales the way dark matter does. It is more like a uniform energy density of empty space, at least in the simplest models. Its main effect is on the overall dynamics of the universe. How fast space expands, how that rate changes over time, and how that in turn affects the growth of structure. In the early universe, matter density was much higher, and dark energy was relatively unimportant. Gravity from dark matter and normal matter could slow the expansion locally and allow structures to form. Over time, as the universe expanded, matter density dropped while dark energy density stayed roughly constant. At some point, a few billion years ago, dark energy began to dominate the cosmic energy budget. From then on, cosmic expansion started to accelerate. That acceleration does not tear apart galaxies or clusters that are already gravitationally bound. Their internal gravity is strong enough to hold them together against the smooth push of dark energy. But it does affect how new structures form and how existing structures grow. In a universe without dark energy, structure formation would continue more efficiently for longer. Halos would keep merging and accreting matter at a higher rate. In our dark energy-dominated universe, the growth of structure slows down. On very large scales, the cosmic web freezes in. Galaxies still merge and interact locally, but the rate drops. Over many tens of billions of years, the accelerated expansion will push unbound galaxies beyond our cosmic horizon. Future observers, far in the future, will see only their local group or local cluster, and the rest of the universe will fade from view. Dark energy, by accelerating expansion, sets the long-term environment in which galaxies evolve and sets limits on how much more large-scale structure can form. So dark matter shapes galaxies from the inside through their halos and local gravitational wells. Dark energy shapes them from the outside by controlling the expansion of spacetime and the supply of new material and new interactions. Both are components of the same underlying theory: general relativity plus a set of energy and matter contents. We do not yet know the microphysical nature of dark matter or dark energy, but we know their gravitational effects quite well. I want to emphasize how we know these things because it is easy to treat dark matter and dark energy as vague placeholders. For dark matter, we have rotation curves, lensing, cluster dynamics, hot gas profiles, cosmic microwave background fits, large-scale structure, and simulations that reproduce observed galaxy distributions. For dark energy, we have supernovae, baryon acoustic oscillations in galaxy surveys, the integrated Sachs-Wolf effect in the cosmic microwave background, and again, consistency with structure growth over time. When we fit all of these datasets simultaneously with a single cosmological model, the so-called lambda CDM model, we get a coherent, quantitative description of the universe on large scales. That does not mean the model is perfect. It does mean that any alternative must match this broad range of evidence at least as well. There are alternatives like modified gravity theories that try to explain galaxy rotation curves and cluster dynamics without dark matter. Some of these, like MOND and its relativistic extensions, can fit rotation curves of individual galaxies quite well with fewer free parameters. But they struggle with cluster mass profiles, gravitational lensing, and the cosmic microwave background all at once. In practice, most cosmologists find that adding dark matter as a real component is a more successful and flexible approach. That said, the door is not closed. If we directly detected dark matter particles in the lab, that would strongly confirm the dark matter picture. If we failed to detect anything in a wide range of plausible models, and if astrophysical tensions grew, we would have to take modified gravity more seriously. At the moment, the balance of evidence still strongly favors dark matter as a physical substance. So what is dark matter physically? The honest answer is that we do not know. It is not made of ordinary atoms. It does not interact with light, except through gravity, and maybe through very weak non-gravitational forces. Many candidates have been proposed. Weakly interacting massive particles, or WIMPs, were long a leading idea. Axions, very light particles originally proposed to solve a problem in quantum chromodynamics, are another. Sterile neutrinos, hidden sectors, and more exotic possibilities also exist. Experiments deep underground in space and at particle accelerators have been searching for signals of these particles for years. So far, no conclusive detection. That lack of detection pushes us to reconsider which parameter ranges and which candidates are most plausible. But it does not yet rule out dark matter itself. The gravitational evidence is too strong. Interestingly, the details of the dark matter particle can affect small-scale galaxy structure. For example, if dark matter is warm rather than cold, it would have a non-negligible velocity in the early universe, which would erase small-scale fluctuations. That would reduce the number of small halos in dwarf galaxies today. If dark matter self-interacts, it can scatter and thermalize in halo centers, changing the density profiles. If dark matter is ultralight, forming a kind of quantum wave, it could produce cores instead of cusps in small galaxies. Observations of how dark matter shapes galaxies on the smallest scales, like in dwarf spheroidals and low-surface brightness galaxies, can therefore act as a laboratory for dark matter physics. On the other side, dark energy's physical nature is even more mysterious. The simplest model is a cosmological constant, a constant energy density of the vacuum. In that case, dark energy does not change with time or space. More general models involve a slowly rolling scalar field or modifications of gravity on large scales. Observationally, we measure the equation of state parameter, W, which is the ratio of dark energy pressure to its energy density. For a pure cosmological constant, W equals -1. Current data are consistent with W very close to -1, within a few percent. Future surveys aim to measure this more precisely and to see if W evolves with time. If it does, that would point to new physics beyond a simple cosmological constant. The fate of galaxies and of the universe depends on these details. In a cosmological constant scenario, the universe continues to expand exponentially. Galaxies in bound groups and clusters remain together, but isolated galaxies drift away, and the observable universe becomes more and more empty from any given vantage point. In more extreme dark energy models, such as phantom energy with W less than -1, the acceleration could grow so strong that even bound structures are eventually torn apart. That is the so-called Big Rip scenario. Current observations do not favor such extreme behavior, but they do not rule it out completely. In other models, dark energy might fade away or even reverse sign, leading to a slowing of expansion or a future collapse. For now, the simplest model, a constant dark energy density, remains consistent with all data. From the perspective of galaxies, the key point is that we live at a time when dark matter still dominates on small scales, and dark energy dominates on the largest scales. Galaxies are still forming stars, still merging, still evolving inside their dark matter halos. But the large-scale cosmic web is no longer growing as fast as it once did. Over very long times, star formation will decline as gas is used up or heated. Black holes and stellar remnants will dominate. The dark matter halos will still be there, providing the gravitational backbone of these fossil galaxies and clusters, even as the universe expands around them under the influence of dark energy. Throughout this story, gravity and spacetime are the framework. General relativity tells us that mass and energy curve spacetime, and that curvature tells matter how to move. Dark matter curves spacetime in and around galaxies. We see that curvature through gravitational lensing, through the orbits of stars and gas, and through the dynamics of clusters. Dark energy affects the overall curvature of spacetime on the largest scales, driving accelerated expansion. When I say dark matter shapes galaxies, I literally mean it shapes the space-time geometry in which galaxies live. The stars and gas follow geodesics in that curved space-time. The dark matter halo defines the well in which the luminous parts sit. Despite all this progress, many questions remain open. We do not know what dark matter is made of. We do not know why dark energy has the value it does, or whether it is truly constant. We do not fully understand how feedback from stars and black holes interacts with dark matter to shape galaxy cores and outskirts. We see some tensions between predictions of the simplest cold dark matter model and the observed abundance and internal structure of small galaxies. And we are still sorting out whether those tensions point to new dark matter physics or to complex baryonic processes. We are mapping dark matter with ever greater precision using lensing and stellar dynamics, but our maps are still relatively coarse compared to the fine structure we would like to see. So I end with one unresolved mystery that sits right at the heart of this topic. When we simulate galaxies with cold dark matter, we predict a huge population of small dark matter subhalos, many more than the number of observed dwarf galaxies around galaxies like the Milky Way. Some of those subhalos may simply be dark, with no stars. But do they really exist in the numbers we expect? Are we missing many faint dwarfs? Or is the dark matter behaving differently on small scales than our simplest models assume? The answer to that question will tell us not only how dark matter shapes galaxies, but also what dark matter itself might be.